In the previous class, we saw a way through which the waves on the transmission line, that is the forward wave and the reverse wave, they superimpose on each other and form something we saw as what is called as the standing wave. Now, a perfect standing wave is formed, we saw, for a very special case of gamma equal to 1, that is for an open load. It will also be formed when you take gamma L equal to -1, that's a short load. Now these are the two conditions when no energy is delivered to the load, the whole of the energy or the power sort of reflects back. So that's a very undesirable condition. Now when we were dealing with this in the previous class, we saw that to know the relationship for the voltages and currents on a transmission line, it was helpful to sort of represent them using a complex phasor. So if you remember, for a lossless line, we had said this. We had derived that V of L is nothing but V plus e raised to j beta L 1 plus mod of gamma L e raised to j phi L minus 2 beta L, where phi L is the phase of the complex load reflection coefficient. So we had established that the magnitude of the voltage, or what is mod of V of L, this will reach a maxima whenever this phase angle, that is phi L minus 2 beta L, is any even multiple of pi. We had drawn this using a phasor diagram. Whereas this voltage magnitude will be a minima when this phi L minus 2 beta L phase angle is equal to odd multiple of pi. This we had proved in the previous class. So therefore, now that we have actually derived the conditions for maxima and minima, let us actually write what they will be. So the maximum magnitude of V of L will be what? This complex exponential will become a 1, V plus, and if you substitute this phase as any even multiple of 2 pi, then in that case this will be nothing but 1 plus mod of gamma L. This is VL, magnitude maxima. Similarly, the minima will be obtained when you substitute this angle with any odd multiple of pi, and you will get Is that fine? Okay. Now, let's define a ratio called as rho, which is nothing but the ratio of the maximum to the minimum magnitudes of this voltage. So that will be nothing but now this ratio has a rather special meaning. This is called as VSWR, or what we call as the voltage standing wave ratio. So just by looking at this nature of rho, we can immediately make a few conclusions. The first is that rho is always real, because we are dealing with magnitudes. And what else can we say? What is the range of values which rho can take? What is the minimum value rho can take? The minimum value rho can take will be when mod gamma L is 0. That is for a match load. So this 2 essentially will become 0 and rho will be 1. What is the maximum possible value that rho can take? The maximum possible value that rho can take will be when mod gamma L becomes equal to 1. That is for an open load or a short load. So in that case, the denominator will tend to 0. So therefore, this rho ratio will tend towards infinity. So I can say this is the range of rho, corresponding to the range of mod gamma L, that is from 0 to 1. Is that fine? So in many applications you will see that while we are very interested to know what is gamma L or the reflection coefficient of the load, it is a more often practical approach to measure the rho or the VSWR. Why? Because first of all, VSWR is real. So if you know that, you can estimate a good amount of what the load is. So the closer the value of rho is to 1, you know that better is the load. The higher the value of rho, you know worse is the load. So in industry, many applications, they'll tell you, okay, let's design, or I want you to design this system for me using a transmission line and a load, but I want the rho to be below 2. Achieving rho of perfect 1 is near impossible. So therefore, we have to be content with some range of rho. So generally, for certain applications, rho less than 2 is acceptable. For some applications, they want more stringent, like rho below 1.5 or 1.2, some such thing. The other thing is that since magnitude of gamma L lies between 0 and 1, measuring of this magnitude may often have errors. Obviously, because we are measuring values which are between 0 and 1, if you look at the whole number line, 0 and 1 are very close. Well, not that we cannot measure it reliably, we definitely can. But there is always the high risk of measurement error in mod gamma L. Whereas if you look at the range of rho, it is 1 to infinity. So therefore, the measurement of rho will always have lesser error as compared to the measurement of gamma L. So therefore, this is one more reason why many people and many applications prefer the measurement of rho over gamma L. Of course, there are many applications where rho is not sufficient. You have to measure gamma L. But as far as possible, many people try to measure rho first. So if I now look at this, I can simply again derive what is corresponding to the voltage maxima. We proved that we get a current minima. You cannot have voltage maximum or current maximum at the same time, or at the same place, so to speak. Whenever this phase becomes equal to even multiples of pi, you get a VL max and an IL min. So this is nothing but and likewise, when you have VL min, you get IL max. So, whenever voltage magnitude reaches a maxima, current magnitude reaches a minimum. So at that point, we get the maximum impedance. So I can say Z max at that point is nothing but VL max by IL min. Remember the mod, it's very important. So if you take the ratio, V plus and V plus mod will get cancelled. You will see this is nothing but Z0 times 1 plus mod gamma L by 1 minus mod gamma L. Now this ratio we already know, it is nothing but the VSWR. So therefore this is rho times Z0. Similarly, Z min or the minimum impedance magnitude on the line is achieved when you have a voltage minimum and a current maximum at the same point. So this is nothing but VL min divided by IL max. So what would this be? You will get this is nothing but Z0 times 1 minus mod gamma L divided by 1 plus mod gamma L. Again, this is nothing but 1 by rho. So this is Z0 by rho. So to summarize this part of our discussion, if you know the VSWR, you can very easily find out what is the maximum and minimum impedance that the line can see at any point. It is that easy. So rather than using those complex formulae of the impedance transformation relation with all those Z0, ZL, sine, cos and whatnot, and then differentiating it with respect to something and finding out the maximum and minimum, you can simply know the VSWR, which will give you the maximum and minimum impedance, given that you know what is Z0, which we always know. So this is a very important relation. So higher the standing wave ratio or higher the rho, worse is the load. Lower the standing wave ratio, better is the load. Which means that if your standing wave ratio is low, it has less chance of forming a standing wave, and therefore more power is transmitted to the load. Now in the previous class, we had drawn the standing wave for an open load. So if you remember, we had drawn how the voltage was varying as a function of length for different instants of time. So let us draw the magnitude, mod V. We had sort of done this. We had taken a cos wave and we had proved that essentially the wave amplitude essentially vibrates. So these are the nodes and these are the antinodes. So you can always, the wave will essentially at different points of time oscillate with different magnitude. But this is the maximum. Remember, unlike last time, I am showing you the mod only. Actually, it will go even negative. So I can say that this is mod V max. And this is mod V min. So this is nothing but mod of 2V plus, and V min is nothing but 0. So if you simply take a ratio of maximum voltage magnitude by minimum voltage magnitude, you will see that the VSWR or the rho for open is nothing but 0, which tends to infinity, which further proves that an infinite standing wave ratio is for open load. This is without using any of those relations using mod gamma L. So likewise you can do for other loads also. However, for loads which are not equal to open or short, it is a little difficult to analyze them with hand. So I encourage that you all can write a MATLAB program or any other program which will actually plot the standing wave pattern for that given load, and using that you can measure the maximum and minimum voltage. In that case, the nodes will not be 0. There will be no clear nodes or antinodes. The antinodes will vibrate with some magnitude, while the nodes will also vibrate with some magnitude, which may be different. So this is one thing. Now, we had defined rho as now when mod gamma L is 0. What that means? This means that it is a match load because there is no reflection. So as we know, for this rho will become 1, which is the most ideal case. But what does this mean from a standing wave angle? What is mod Vmax and what is mod Vmin? So since we define rho as mod VL max by mod VL min, the two will be equal. You will essentially see that one wave is propagating towards the load and nothing is coming back. So there will be no concept of nodes or antinodes in such a case. The maxima and minima of the voltage as a function of the length of the line at all given points will be the same, because it's going to be a traveling wave. You cannot say that, okay, this particular point will always be at this voltage. No, you cannot say that. So therefore, this particular case for a match load, why do I say match load? Because in this particular case, ZL will be equal to Z0. For this particular match load, there will be no standing wave. So the entire energy of the wave is absorbed by the load. This is very important. So is that fine? So therefore, the VSWR is a very important factor, and it is often measured very frequently in case of transmission line applications. Now, let us go back to a quantity which we introduced 2 classes back, that is the normalized impedance. So using normalized impedance of the load, I can define my ZL as Z, or my gamma L as ZL minus Z0 divided by ZL plus Z0. In terms of the normalized load impedance, where I can put small zl is nothing but capital ZL by Z0. This will be small zl minus 1 by small zl plus 1. Now, at any point on the line, I can have impedance Z as a function of L, and I can normalize it and call this as small z, which is nothing but Z of L by Z0. So, reflection coefficient at any point L, reflection coefficient at any point L, that is gamma of L, is nothing but Z minus 1 by Z plus 1. So this is something which we can write as a function of normalized impedances. So what you see is that the impedance or the normalized impedance is a dimensionless quantity. So the ratio of two dimensionless quantities gives us something which is also dimensionless. Now, look at these two terms, the numerator and the denominator. What is the degree or the order of this two algebraic terms? They are both first order. That is, in some sense we can say linear. It's not truly linear because of this plus and minus 1, but since it's first degree and you are not very concerned about where the origin is, we can say that okay, if that is the case, we can call them linear. Even the denominator is linear. Hence, if I have a ratio of two terms which are both first order, then this kind of a relation is called as a bilinear transformation or bilinear relation. Notice that I have used the word transformation. Why? Because these two terms are denoting impedances, and this term is denoting some other complex number which is not impedance. Well, it's a function of impedance definitely, but it's not impedance. It's the reflection coefficient. So transformation from impedance values to gamma values, where gamma is the reflection coefficient. You can correlate it with this expression also. So now let's go back and write gamma, which is nothing but Z minus 1 by Z plus 1. So Z is the normalized impedance at any point L, and this we can write in a Cartesian form as R plus J small x, where small r denotes the normalized resistance and small x denotes the normalized reactance. So x can be negative also, depending on whether it's inductance or capacitance. This you know. So now we can write that we can represent in a polar form like how we did in the previous class, where mod gamma is the magnitude of the reflection coefficient and phi is the phase. Remember, even though we are normalizing it, the quantities may remain complex. So this is nothing but is that fine? Now, we are denoting the impedances using a Cartesian axis. So therefore, let us draw the Cartesian plane. So the real axis is R and the imaginary axis is Jx. Now, in this 4-quadrant Cartesian plane, which quadrants are of interest to us? Can we have impedances everywhere? Not really, because my R is generally positive. So that means on the real axis, this particular left hand side is of no use to me. So what is of interest is starting from 0 to infinity. What about x? X, there is no such constraint. You can have positive x if it is an inductor, negative x if it is a capacitance. So therefore, the first and fourth quadrants are important to us. Can we have negative resistance? Well, there are certain very special cases when we can actually have resistance which is negative. But that discussion is for another day and time. And it's beyond the scope of this course. But I encourage you all to read up about applications where negative resistance can be encountered. Now, this is a Cartesian plane. Let us look at this. The gamma, which I have expressed in the polar form. I have expressed gamma in the polar form. So, what is mod gamma max? Or what are the range of values mod gamma can take? What is the maximum possible value gamma can take? It's 1. What is the minimum possible value gamma can take? 0. So, this is what we know. Gamma is a complex number. So, this is what we call as the, before I go over here, let me just label this as the impedance plane. Since gamma is also a complex number, let me denote something called as a gamma plane. This is real, this is imaginary. I can say that all values of gamma will lie between 0 and 1 because we have proved that. We know that because of this relation, the values or the range of values which gamma can take have a bound. But where can the gamma values lie? Gamma minimum is 0, that is here. Mod gamma equal to 1 can be anywhere. It can be here, it can be here, it can be here, here, or any other point in the middle. So how can we represent this gamma? We can represent the gamma max by using a circular contour. Which is 1. So I can say that if I have an impedance plane, or if I have some value of impedance, the corresponding reflection coefficient, if I map it on the gamma plane, will always be bound in this region, inside the circle. Is that fine? Whatever be the value of resistance, or sorry, the impedance, as long as the R is positive, you can prove, or we have proved that the gamma values will lie between 0 and 1. So if you look at the graphical way of representing it, it will lie inside this unit circle. It's also called as the unit circle, because the radius is 1. Any mod gamma equal to 1 vector will have the circle and the radius of 1. Is that fine? So now let's get to business. We had defined impedance Z as R plus Jx, or the normalized impedance. Let us define gamma as U plus JV. So I am representing gamma in both forms, Cartesian as well as polar, so that you know that that's possible. Now let us write the transformation relation. Gamma is nothing but, and this is the way we transform. Now let us investigate case by case. What happens when Z is purely real or purely resistive? That means the imaginary component Jx is 0. So if that is the case, all the possible values can lie on the R axis. So if my Z is real, what are the values which gamma can take? So let's take case 1. What is the possible value of R? Infinity. 0 to infinity it can be. So what is the possible value gamma can take? The minimum gamma will be -1 and the maximum will be +1. I can also say that since both numerator and denominator in this case will be real, gamma will also be purely real. So therefore 0 becomes -1 and infinity becomes +1. Notice this is something very interesting. What was infinity on the impedance axis or the impedance plane, I am now representing it as a point on the gamma plane. So yes, infinity in some sense can be captured. Yes, we are doing that. So whatever are the possible values here, they will lie on the real axis. So real values get mapped to the real axis in the range -1 to +1. Is that fine? Next, what if Z equals Jx? That means it's purely imaginary. R is 0. That means all possible values lie here on the vertical axis. Now what will that be? On the gamma plane. So in this case, gamma will be Jx minus 1 by Jx plus 1. So as you can see, in general it will be a complex number. But can we say something about this? Yes, we can. Yeah, we cannot say about the phase, because to know the phase, we will need to know the value of x. But we can definitely say something about the magnitude. The magnitude of the two complex numbers will always be equal. Therefore, the ratio of the magnitudes will always be 1. That means if Z equals Jx, then all those possible impedances will lie on the unit circle, mod gamma equal to 1. And you can very easily prove that if x is positive, that is this part, all the positive x values will get mapped onto the upper periphery of the circle, and all the minus jx values will get mapped into the lower periphery. So this part denotes inductive reactance and the lower part denotes capacitive reactance. Why? Because this is minus Jx and this is plus Jx. Now, if I look at this point, plus 1, gamma equals plus 1. So, which load we know has a reflection coefficient of plus 1? It is open load. So, therefore, this point plus 1 corresponds to an open load. This point minus 1 corresponds to short. So, the third case, if I say general case where z equals r plus jx, it can have both real as well as imaginary parts. So in that case, all of them will lie at some point which is inside. Now that you have to map out. Now this is something very interesting. We have taken two axes, one non-negative from 0 to infinity, that is the r-axis. The other is the minus infinity to plus infinity x-axis or the reactance axis. And what was infinite, we have captured them all in this periphery. We have captured this in this periphery. So this circle denotes or has a cluster of points inside it. If you look at this relation, gamma equals z minus 1 upon z plus 1, it is a bilinear transformation. Now if you go back to your mathematical basics, what can be said about this transformation? Is it a one-to-one mapping? Is it a many-to-one mapping? You can prove that this will be a one-to-one mapping. That means for every distinct point on the impedance plane, there exists a unique point on the gamma plane also. This is something very interesting. Any possible distinct impedance point can also be represented in a distinct manner inside this gamma plane or inside the circle in the gamma plane. So, this forms the basis of what we call as the Smith chart. This representation of all possible impedance points but on the gamma plane is the Smith chart. So let's write this down. So this study was done, I believe, in the year 1939, so which is over 8 years back. It was done by this scientist called Philip Smith, and thanks to him, a lot of the headache of having to remember all those difficult, tedious, mind-boggling formulae for transmission lines, they have been reduced by a lot. So this Smith chart essentially gives you a graphical technique to solve a lot of these problems. So let us see how to make the Smith chart, or how this Philip Smith, he actually developed this chart. Now what do we want to do? We want to represent all possible impedances on the gamma plane That means we will draw the gamma plane and we will mark those points where the reflection coefficient gamma for the corresponding load we want to represent will come here. Okay, so that means on the gamma plane I want to represent impedance. So we know the relation between gamma and z, or gamma and small z. Here I should say only for normalized impedances. Because we have been working with normalized impedances when we were discussing the mapping. We know that it's a one-to-one mapping. So can we represent z in terms of gamma? Yes, z will be 1 plus gamma by 1 minus gamma. Note that this is not the same as VSWR. VSWR is 1 plus mod gamma divided by 1 minus mod gamma. That is a totally different thing. Okay, so on the gamma plane I want to represent this impedance. So let small z be r plus jx and gamma be u plus jv. So I can write over here r plus jx equals 1 plus u plus jv divided by 1 minus u minus jv. You can normalize this. You can normalize this, or you can rationalize this by multiplying the complex conjugate of the denominator on both numerator and the denominator, and you will get something like this. So if you multiply two complex numbers or a complex number with its conjugate, you will get this. The j is not there. So now you have a Cartesian term on the left hand side. So therefore I can also split this term into a real part and an imaginary part. So if you do that, you will get something like this. So if I equate the real and imaginary parts, this corresponds to r and this corresponds to jx. So if I write and over here, or rather let's start with r. So now let us not forget what we are trying to do. We are trying to map the r point onto the u and jv axis. So if I now simplify this, I am going to get something like this. You can do this very easily by a little bit of algebraic manipulation. If you are a little confused, you can refer the handouts which are accompanying this lecture, but I am not going to show all the parts in the lecture. So if you just manipulate this is what you will get. What does this equation signify? This signifies a circle on the gamma plane. Or I should not say circle, I should say a family of circles. Because R can be anything. On gamma plane, whose center is R by R plus 1 comma 0, because this has no minus term. And the radius is 1 by R plus 1. That means every given value of R will correspond to a circle with given center and radius. So a given value of R will have a distinct circle. So therefore, this is called as the constant resistance solution. Let us see what this circle looks like. Now, I have, this is my U axis, this is my JV axis. Let's first put simple, R equal to 0. So if R equal to 0, the center will be 0 comma 0 and the radius will be 1. So if the center is 0 and radius is 1, what will it look like? It will be nothing but the unit circle. Please note that R equal to 0 does not mean Jx is equal to 0. Jx can take any value, because we have not yet solved for that. So this contour indicates only those impedances which have R equal to 0. Jx can be anything. Please remember that. Until and unless you know both R and Jx, you cannot zero down on a point. If you know either R or either Jx, you can only get a contour. You can never get an exact point. So now let's take the second case. R equal to 1. So what will the center be? The center will be 0.5 comma 0 and radius will be 0.5. So the center will be somewhere over here. This is 1, this is minus 1. What about when R equals 3? So the center will be 0.75 comma 0 and the radius will be 0.25. So it might look something of this kind. So 0.75 will be somewhere over here. Yes, this is what it will look like. So what you can see is that something very interesting. All the circles have their center on the real axis, on the gamma plane. and as the value of r increases, the size of the circle keeps decreasing and it moves towards the open circuit. So therefore r is equal to infinity will be a point which is nothing but the open. Now this is the solution for the constant resistance. Let us quickly do it for the constant reactance also. So if you just recall, this was what was for Jx. If you quickly do some algebraic manipulation, this is what you will get. So this is again a family of circles whose center is 1, 1 by x and radius is 1 by x. Now what will they look like? The center will lie on the u equals 1. It will lie on the u equals 1 line. So let us take case 1. That means the center is 1, 1 and the radius is also 1. So 1, 1 will be somewhere over here, and the radius is 1 means the circle would look something like this. It's going to sort of be like this. Likewise, if I have x equals minus 1, the center will be 1, minus 1 and radius will be 1. So in that case, the center will be somewhere here and now there's a reason why I am not drawing the full circle. We shall know that very shortly. The reason I am not drawing the full circle is because most of the circle on this side, they lie outside the unit gamma circle, and that's of no use to us. So this is what I'm showing you. So now let x be 2 and x is minus 2 as the second case. So the center will be 1, half, and here the center will be 1, minus half, and the radius should ideally be mod x. Yeah. So 1 by mod x, yes. So the radius in this case will be half, and in this case will also be half. So what will that look like? 1, half will be here, and 1, half minus half will be here. So therefore it will look something of this kind. the circle will be smaller. So as the mod of x increases, the circles, the centers keep shifting downwards for inductances and upwards for capacitances. So the centers keep shifting as x increases. So the circles keep getting smaller and smaller. Something of this kind. So if you now superimpose the constant resistance solution and the constant reactance solution into a single gamma plane, you get this. So these bold ones are the constant R circles and these are the constant X circles. You can also have circles with smaller x. I've just taken some examples. So, using the bold line and the dashed line, we have made a coordinate system where we can map any impedance we want on the gamma plane. And this is nothing but the Smith chart. Remember, we have made a new coordinate system, a new graph. It just doesn't look like a graph so much because we are used to having linear axis. These ones have circular axis, but the meaning remains the same. It's going to be a very, very, very useful tool. So we will stop here for today. Thank you.